Okay, let's dive into this. Have you ever watched a swarm of drones lighting up the night sky? Or, maybe you've seen one of those videos of an automated warehouse, the ones where hundreds of robots are just zooming past each other? And you probably wondered, how on earth are they not crashing into each other? Well, today in this explainer, we're going to unravel the absolutely fascinating intelligence that actually makes all of that possible. We are looking at a real game changer here, a groundbreaking AI framework called LC MAPF. That stands for Local Communication for Multi-Agent Pathfinding. And over the next few minutes, we're going to see exactly how these robotic swarms are literally teaching themselves to communicate.
Now, to anchor all this abstract math to reality, let's just picture a physical workspace for a second. Think about the aisles of a massive automated warehouse, or even autonomous cars navigating public roads. For robots to even begin moving around, they fundamentally need a valid infrastructure. Imagine driving down a narrow one-way street that just doesn't have an exit. That's a non-valid space, right? You'd inevitably get completely trapped. A valid layout simply means robots actually have the physical clearance to get from start to finish without passing through each other in physically impossible ways. So before we even touch on the brain of the robot, the physical world it operates in has to allow for safe passage.
But even in a perfectly designed space, we face a monumental challenge. Think about it. How do hundreds of independent robots navigate a shared environment all at once without causing a massive pileup? I mean, this is the core challenge of modern logistics. It is not just about getting from point A to point B. It's about doing it quickly, efficiently, and safely, while 100 other agents are trying to do the exact same thing at the exact same time. That's the core problem we are going to solve, step by step, today. So the crucial point is, we're going to build this complex concept up piece by piece so it makes perfect sense. We'll start with the robot traffic jam, move into thinking in snapshots, explore the transformer brain, compare centralized versus decentralized systems, break down exactly how LC MAPF works, and finally, look at the future of teamwork.
All right, part 1, the robot traffic jam. Let's establish exactly what we're up against.
In computer science, this whole traffic jam problem is officially known as MAPF, multi-agent pathfinding. On the surface, the definition sounds, well, incredibly simple. Just find collision-free paths for multiple agents from their start to their goal. Simple enough, right? But mathematically, it is an absolute nightmare. Look, if you have two robots, calculating their path takes a split second. But add 10 or 50 or 100. The math doesn't just get a little bit harder, it completely explodes. The number of potential collisions creates a web of possibilities so massive that even the most powerful supercomputers in the world would take years to calculate the perfect route for everyone simultaneously. Computer scientists actually call this an NP-hard problem. It creates a massive, massive computational bottleneck.
Which brings us to part 2, thinking in snapshots. How do we get around that bottleneck? Well, if looking at the entire map all at once is just too mathematically heavy, we have to change the rules of the game. We change how the individual robots perceive their world. To make this fast, we rely on a concept called the Markov property. The best way to think about this is like amnesia with perfect present awareness. Imagine you're navigating a super dense, bustling crowd in a subway station. You aren't thinking about the route you took 10 minutes ago, right? And you definitely don't have a drone giving you a top-down view of everyone in the building. You're just looking at the people immediately in your little bubble, making step-by-step decisions to dodge them. That is exactly how this local observation setup works for our robots. A robot only looks at a small local patch around it, typically just an 11 by 11 grid. It makes its next move purely on what's in that tiny square, right at this exact second. It's just a snapshot in time.
Moving on to part 3, the transformer brain, because a snapshot is completely useless without a brain to process it.
Taking a snapshot is really only half the battle. The robot still needs a brain to decide whether to move forward, turn, or just wait. And this is where machine learning has completely revolutionized things. Before this new LC MAPF model even arrived, researchers had to build a foundation model to act as that brain. To make this AI smart, they used a technique called imitation learning. Think of it like a teenager learning to drive by just intensely watching their parents. The AI doesn't instinctively know the complex rules of warehouse navigation. Instead, it watches a master algorithm, in this case, a slow but highly accurate traditional solver called LogCam. And it watches this expert solve puzzles perfectly 1 billion times, yet 1 billion observation action pairs. By watching 1 billion examples of perfect driving, the neural network learns to recognize the patterns of success and just imitates that expert behavior. Now, the brain actually processing all this data is a transformer neural network architecture. By the way, that's the exact same underlying tech that powers things like ChatGPT, but instead of reading text, it's reading physical space. And it does this in 3 crucial steps. First up is tokenization. AI can't see a picture the way you and I do, so it takes that 11 by 11 visual grid and chops it up into digital puzzle pieces, or tokens, kind of like how ChatGPT turns a sentence into individual words. Step 2 is positional encoding. Without this, the AI just sees a meaningless jumble of pieces. Positional encoding adds spatial coordinates, like an X and Y axis, so the robot knows exactly where an obstacle is. Finally, step 3 is the attention mechanism. Imagine you're at a really loud cocktail party. You naturally tune out the background noise and attend only to the voice of the person right in front of you. The robot's network calculates mathematical weights to do exactly that, deciding which nearby agents are on a collision course and which ones it can safely ignore.
Okay, part 4, centralized versus decentralized. Why do we need to upgrade this awesome transformer brain even further? To understand why a new innovation was desperately needed, we have to look at the 2 main philosophies in robot pathfinding. The classic approach is centralized planning. This is like having a single, all-knowing air traffic controller dictating every single move for everyone. It gives you perfect collision-free coordination, but man, it scales poorly. It's just too slow. Add 1,000 robots, and that one controller gets completely overwhelmed. On the flip side, we have decentralized planning, where each robot uses its own individual transformer brain. It's lightning fast, it scales beautifully, but there is a huge catch. The agents are completely silent. They are totally blind to each other's intentions. So when 2 of these blind robots hit a narrow hallway, they might both step forward, realize there's an obstacle, step back, and step forward again. They get stuck in this endless awkward dance, a total deadlock, simply because they can't say to each other, "Hey, I'm coming through, you go first."
This brings us to part 5, how LC MAPF works, the real game changer.
We desperately needed a way for these decentralized lightning-fast robots to negotiate with each other locally. Enter LC MAPF. Now, what's really interesting here is how elegantly this 3 million parameter model solves the communication problem. If robots tried to send their entire highly detailed 3D maps to each other, the warehouse Wi-Fi would instantly crash from the bandwidth overload. No way that works. Instead, LC MAPF uses an information bottleneck, which is actually inspired by something called the perceiver architecture. Imagine taking a giant 1,000-page epic novel and boiling it down into a 3-sentence summary. That summary is called a latent state, a tiny, ultra-compressed packet of just the essential data. The robots beam these tiny summaries to each other. Then they use a process called cross-attention decoding to stitch their neighbors' summaries together with their own map. This creates a flawless, shared understanding of the space without ever having to transfer all that heavy, bulky data.
But hold on, because here is the most mind-bending part of LC Math: unsupervised messaging. When the researchers built this, they didn't give the robots a dictionary. There are literally no pre-programmed words for stop or go or turn left. Instead, the researchers basically just told the AI, hey, don't crash and get to your goal as fast as you can. Because gradients flow directly through the action loss, the AI naturally learns what to communicate just by trying to avoid collisions. Through millions of rounds of trial and error, the robots just started sending random strings of numbers to each other. And when a certain string of numbers successfully prevented a crash, the AI remembered it. Over time, these random strings evolved into a highly specific, complex mathematical language of negotiation. It's a language humans can't even read. It was entirely invented by the machines themselves just by trying to stay out of each other's way. How crazy is that?
And honestly, how much talking do they actually need to do? Exactly 4 rounds. That's it. Before taking a single step forward, the robots pass these compressed messages back and forth exactly 4 times in mere milliseconds. It is an entire debate, compromise, and finalized traffic plan, all happening in the blink of an eye, way before any physical wheels even turn on the warehouse floor.
Finally, part 6, the future of teamwork. Let's look at the big picture.
We've covered the technical brilliance under the hood, but what does this mean for the real world? Well, it all comes down to scalable, real-world coordination, and this brilliantly illustrates the ultimate triumph of LC MAPF, linear scalability. Remember how in old centralized systems, adding 10 robots might make the system 100 times slower? Well, with LC MAPF, because the robots are only whispering to the guys directly next to them in those 4 quick rounds of local communication, the central computer does not care if there are 10 robots or 10,000 robots. The computational burden never changes. You could literally drop thousands of robots into a massive logistics center, and they will simply act as this fluid, highly intelligent swarm, perfectly avoiding traffic jams without ever slowing down the overall system. It is absolutely incredible to see how AI is shifting from just, recognizing patterns to actively collaborating and problem-solving together in physical space. We've seen how blending concepts like the Markov property, transformer brains, and unsupervised messaging can seamlessly solve complex logistics. Which really leaves us with a pretty thrilling question to end on. If AI can learn to invent its own language without any human supervision, just to avoid traffic jams, what else will robot swarms teach themselves next? Thanks so much for exploring the mechanics of multi-agent pathfinding with me today in this explainer. I'll catch you in the next one.